Welcome back, Lecture 49, Math 141. We are in the middle of Chapter 5, Section 3, Evaluating Definite Integrals. The kind of the most important part as far as how to get an antiderivative and evaluate it at the upper limit. Subtract from that the antiderivative evaluated at the lower limit. We are past that. We've got a lot of kind of more complicated integrands to deal with and to break down and to look at in pieces and those kind of things. But the basics to it we have. I intended to do this yesterday, but just got pushed aside by other things we had to do. I wanted to make some comments in general on the most recent test, Test 3. I kind of have to be careful when I make comments on the test because the cable TV class is about 4 or 5 lessons behind this, so I don't want to talk about the test before they've actually taken the test, but they've taken the test now. Just some things in general that I noticed on problem 2. This is test number 3. Problem 2, and I wasn't trying to make this a trick problem by any means. We've got a radar station right here, and the plane is flying directly over the top of the radar station. And that distance is 1 mile. And obviously the plane keeps going in this direction. So there are 2 things that change in this problem. Not the 1, that's fixed, but the plane flying out here, and we are given that rate, and then the distance between the plane and the radar station. And believe it or not, that was probably the most frequently missed thing, is that in the problem, let me read the problem. A plane flying horizontally at an altitude of 1 mile and a speed of 300 miles per hour passes directly over a radar station. So that's where it is. Obviously, it keeps moving. Find the rate at which the distance from the plane to the station, that would be this distance. So this is the plane moving off to the right, or not necessarily to the right, but that's the way I've pictured it, when the plane is 2 miles away from the station. So here's the plane, here's the radar station, so it's when x equals 2. So your little triangle, kind of at this moment triangle, this is 1 mile, this is 2 miles, and then it's your task to find that distance. So believe it or not, probably the most common error was that people had capital P equal to 2 instead of, on this diagram, the hypotenuse, or x equal to 2. So I think this ended up being, what, square root of 3? And your Pythagorean triple here was 1 squared plus p squared equals x squared. Let me point this out too, and some of you did this and you did it correctly, but be careful when you take something in a related rates problem that is fixed and you call it a letter. So some of you, let's just call that A. And if you derive with respect to t, that's fine. You've got 2a dA over dt plus the rest of this stuff. What is dA over dt if a is fixed? It's 0. So some of you did that, and it's okay to do that as long as you recognize that it's constant. It's not changing at all. Its instantaneous rate of change is 0. So it's okay to call it a letter even though it's fixed, as long as you realize its rate of change is 0. Another comment. Problem number 3, I did kind of apologize ahead of time for the fact that the numbers were going to be large in magnitude, or very large positive, very small negative numbers. It still worked out. But some of you on number 3, part of finding absolute max and absolute min are to find the endpoints. So the endpoints on this problem, so it's -5 something and 14 something. And how do you find those somethings? Plug them into the function. So we need the function evaluated at -5 and the function evaluated at 14. That was, I thought, kind of almost like a gift on this problem, but some of you rejected my gift and decided that you didn't want my gift and did not include that in your problem. One of those, I can't remember right now, is the max. So this one is the absolute max for this particular problem. So it occurred at the point 14, 360. I could tell that some of you were doubting which answer to give. What's the max? Is it 14 or is it 360? So you gave both. That was smart because that's where the maximum occurred. This is the maximum, 360. That's the highest this function gets on this interval. The only other thing I can remember that hasn't been addressed was on problem 4. You had, after you put it into the other form, x cubed over e to the x squared. A couple of you did it a different way, and you still did the problem successfully, but this is the way most of you attempted this problem. It is infinity over infinity. Sometimes you can have an idea what the answer is going to be. Did you have an idea what the answer is going to be based on kind of this version of infinity compared to this version of infinity? Which one seems to be larger? The bottom seems to be larger. So if the bottom's version of infinity is a whole lot larger than the numerator's version of infinity, what's your guess at this stage?
0.
0. Okay, which ends up being the answer. But since we have infinity over infinity, you can use L'Hopital's rule. The numerator is not an issue. And you know eventually you're going to get to the point where you have a number, right, in the numerator. Denominator, derivative of e to the x squared is what?
2x.
2x e to the x squared.
Yes.
Is that right? And we still have infinity over infinity. And this is where some mistakes were made. What do we have to do if we take the derivative of the denominator? Have to use the product rule. We do have a product of variable quantities, and a handful of you did not use the product rule here when you had to use L'Hopital's rule again. So the derivative of the top is 6x, derivative of the bottom. Let me just write this down here. That it should be the product rule on this particular product. And granted, it gets a little ugly, but you know you're going to have to do it probably one more time. And some of you started the product rule again, and you said, this is going to be infinity. That's okay, because you knew the numerator was not going to be infinity anymore. It was going to be 6 the next time around, so that's fine. But at least the first time through, I guess this is technically the second time through, but you have a product. So you have to use the product rule in this particular version. I think that's all that I can remember in common, the common errors that I found. All right, let's finish up what is in this section, anyway, about what we can do with the definite integral. We know it finds area under a curve. That's about it to this point. Another application of what the antiderivative, this definite integral, can give us. Notationally, that's a little different than what we've used, but the only difference is I put capital F prime of x here. So if we take its antiderivative, we're back to capital F of x. So this represents the net change, or sometimes called the total change theorem. This is a rate of change. It's a derivative. It's the derivative of capital F. So any derivative is an instantaneous rate of change. Among a couple other things, it's the slope of the tangent. But since it's a rate of change, so we can start with a rate of change and end up then with the total change that you undergo from B to A, whatever B and A happen to be in that particular problem. So in your book, you'll see the net change theorem, or total change as you go from point A to point B, is exactly what I just did. And the reason is because that's a rate of change. When you anti-differentiate a rate of change, you have the total change. Now, how would that come into play on a problem? Let's say, for an example, we have v prime of t. And I don't know what v is. V can be velocity, but it could be something else, too, that started with v. But that's the rate of change of v. And if you start with the rate of change of v, and you anti-differentiate it, what do you come up with? Starting with the rate of change of v. This ends up being the total change in velocity, or whatever v represents. So you can call it net change. I've seen this referred to as total change in v. So you start with v prime, you anti-differentiate, you ought to be back to v. One more example. Let's suppose this is the rate of change of population. It's p prime. So if you start with a rate of change of population, and I guess I could think of it like this, we want the area under the rate of change of population. What's the area under the rate of change of population? It's the net change in population. So you can draw a diagram. But if you start with it rate and you anti-differentiate it, you're back to what that rate of change, that quantity, substance, population, velocity, whatever that happened to represent. There is a specific WebAssign problem that is geared toward this net change or total change theorem. But just pay attention to the wording in it, because it says how much does the population change from time 0 to time 20. So that's what they want. They want you to take that rate of change, integrate it, and evaluate it from A to B. All right, the last thing in 5.3 is when we're dealing with a rectilinear function, something moving along a straight line path. This net change will get us kind of where it ends up. How is that different from where it started? So something that moves along a straight line could do this. Okay, so here's our line. So I'm going to show it so it's not overlapping. So it starts here, and then it moves to the right, and then it stops. Okay, actually it's supposed to be on the line, but I'm showing it so it's not overlapping. And then it moves for a while in this direction, and then it stops. again, should all be in the same line. So it really started here, came to here and stopped, turned and went back here and stopped again, and now it's going to, let's say, go to right here. So all that happens on the line, linear path. So again, starting here, it moves to the right till it gets to here, comes back to the left till it gets to here, and then moves its way back to the right. Now, if you just kind of took this rate of change function and you integrated it and you evaluated it from time 0 to whenever it stopped, let me put some time marks up here. Let's say that's time 0. This is time 3. This is time 5. And this is time 6. So those are the kind of where it is on this line, linear path, rectilinear function. So if we just integrated this rate of change, whatever it is, I'll call it f prime, and we integrated it from 0 to 6, it would tell us the net change. Well, what's the net change? Here's where it started, and here's where it finished. It would give us that. Is that really representative of what happened? Well, in a way it is. It's descriptive, but it doesn't really tell us what happened at all those different places. It tells us where it starts and where it ends, and that's it. So we get this number, whatever that number is, that distance along the line. So that's a displacement. So it's kind of like the net change. Suppose we want the actual distance that it traveled. Well, we'll probably have to break it up into pieces, and we'll integrate it from 0 to 3, and that'll give us that distance. And then we'll integrate it from 3 to 5. This is still a distance, but it's going to the left. It'll add that to it, even though that's negative, right, because it's moving to the left. We'll make sure it's positive by taking the absolute value of it, because we just want distance, total distance. And then we'd also go from 5 to 6. So if we want total distance, we're going to take this function. Maybe it's a velocity function. That would make sense if we wanted distance. And we would go from 0 to 3. That is positive, but just to make sure, we could take the absolute value. From 3 to 5. We think that, based on my diagram, is to the left, so it's probably going to be negative. Let's make sure it's positive by doing that, because we want kind of the distance traveled. We don't care if it's left, right, up, or down. And then at that point it stops and moves to the right again. So from 5 to 6. And again, just to make sure, we'll take the absolute value. So that's going to be a very different number, right, than the final displacement. Displacement is basically where did it end compared to where it started. Total distance is we're concerned with where it stopped and turned and went back the other direction. All right, let's do one example here. Let's say we have a velocity function that is t squared minus t minus 6. And this is in meters per second, are the units. Let's get the displacement. From time 1 second, to the 1 second to the 4 second mark. So where did it end up compared to where did it begin from time 1 to time 4? So when we anti-differentiate a velocity, what should we expect to get? position or height or distance, right? In this case, we're probably going to get a distance, a location. So we integrate t cubed over 3, t squared over 2, minus 6t. We'll evaluate from 1 to 4. So we'll plug in 4, plug in 1. So there's our arithmetic. If we get a positive, what's that mean? The net change says its final resting place is right of where it started. If we end up with a negative, its final resting place is left of where it started. So 4 cubed, 16 64/3, minus 16 halves, which is 8, minus 24. Everything that follows gets subtracted. So subtract a third, add a half, and add 6. What's the net result of all that arithmetic?
Negative 4.5.
What is it? Negative 9 halves?
Negative 4.5.
Okay, negative 4.5. Got some agreement on that. So what did we decide? What are the units for that? Meters, right?
Yeah.
And that means that its final resting place is 4.5 meters to the left of where it started, right? Where it started in terms of where it was located at time 1. Now, how far did it travel during that interval? That's a different problem. Any questions on kind of the net change? So total distance. Well, here's our velocity.
Wait, was that the net change or the displacement?
That was really kind of the net change, in a sense that it moved to the right some, it moved to the left some, it ended up 4.5 units to the left. So now we want a different interpretation. How much total distance did it actually travel? When it was moving right, that's positive. When it's moving left, we still want that to be positive. So what do we need to do with this function? Graph it, and if we were to graph it, what would we want to figure out about it?
Break it up in
We want to break it up in pieces based on where it is,
positive. Yeah, no.
where it stopped, right?
Yeah.
And where it stopped, what is that? What happens when it stops?
It's different.
This is a velocity.
Changes in,
The velocity would be 0,
Yeah.
right? When it stops.
yeah.
So we want to know, when is the velocity equal to 0? Well, here's our velocity function. Does that factor? I hope it does. I think I picked one that factored. So factors of -6, that'll get us -1 in the middle. -3 plus 2. So when the velocity is 0, what are the t values?
3 and -2.
Okay, and which of those do we care about?
The 3.
We care about the 3 because we're concerned about the interval from time 1 to time 4. So the only answer in there is time 3. So apparently it starts one direction. I don't know. What direction is that? What's the velocity at time 1, and then it stops at 3 and changes, more than likely. Could we use a chart that would tell us what it's doing from, really all we care about is 1 and 4. And we know something happens at 3. The velocity is 0. So when you put any value in here into the velocity, what's the velocity at 2? Is it moving right or moving left? You put 2 in here, into the factored form.
So it'd be
Positive or negative?
Positive.
Negative.
Oh.
If you put 2 in there, that piece is
Oh,
negative,
negative.
that piece is positive. So it starts out moving negative, moving to the left, moving negative. I don't know what that means. I guess it means left. And then if you put in a value between 3 and 4, put 3.5 in here and here, what do you get?
Positive.
Positive.
So that means it's moving to the right. Not that it really matters that much because we're going to take the absolute value of both pieces anyway. But that's how this thing, it moves to the left. During the first 3 seconds, it stops at the 3-second mark. It turns and then moves to the right. And we knew the left part was going to win because it ended up 4.5 units to the left of where it started. So to get the total distance traveled, we'll take that velocity and integrate it. Tell me how we're going to do this differently. 1 to 3. Absolute value. Good. Thank you. And then we want to pick up with 3 to 4. And we're pretty sure that's positive, but let's make sure we get either piece, which has the potential to be negative. Let's take care of both of those. So we've already integrated this. T cubed over 3, t squared over 2, 6t. We're going to evaluate that from 1 to 3. Then take the absolute value. T cubed over 3, t squared over 2. Just to make sure, we'll take the absolute value of that. So let's set up the arithmetic and somebody can punch it in. So it's going to be 3 cubed over 3, 3 squared over 2, 6 3s. Put in 1. Absolute value of that. Put in 4. Why is this subtracted? Because we're evaluating it from 1 to 3. So there's 3 and there's 1. Now we'll slide over to this one. Put in 4. And subtract from that what we get at 3. Now, because these are in separate absolute value brackets, we're probably not going to be able to combine some terms that look an awful lot alike, right? We need to do the arithmetic within each bracket and then put those two things together. So the total distance traveled, I heard a bunch of buttons pushing.
I got 2.
You got what?
I got 2.
2?
I think it's 10.17.
It's got to be bigger than 4.5, doesn't
I
it?
got 61 over 6.
Doesn't it have to be more than 4.5?
Yeah.
Because it moved to the left initially, and then it moved to the right, but it still ended up 4.5 units to the left of where it started. So our total distance traveled has got to be larger than 4.5. And what did you get?
10.17.
10.17, so that's 10 and 1/6. Anybody else get the same?
We're doing it right now. I'm in the moment.
And that would be meters, right? I'll wait till we get at least agreement. Not that I don't trust you. I do trust you. It's in the book? Okay, now we trust it. Okay.
It's too much, but I'm
Does that seem logical for an answer? That if it ended up 4.5 units to the left of where it started, that the total distance traveled has to be at least 4.5. More than likely, more than that, because we knew it traveled to the right as well as to the left.
But we don't know where it started.
We really don't. Okay? I guess if we have a velocity function and we wanted to know the position it would be, we would anti-differentiate it and evaluate it at that starting time, which for us is time 1. So where was this at time 1?
-6. No, in the antiderivative, you have to solve for...
Yeah, we would do the antiderivative and then plug in t equals 1. So we could do it.
Yeah,
It's 6 minus a third. I'm sorry,
1/3 minus 1/2.
minus 6. Yes. Okay, questions or issues with that? Okay, some of you walked in late. Make sure I get that changed on my attendance, which I won't change that right now. All right, section 5.4 has the name Fundamental Theorem of Calculus. Does that sound like it might be kind of valuable? The fundamental theorem of life. Okay, does that seem like it might be kind of something you might want to read about? Yeah, this is calculus, and this is the fundamental theorem of calculus. And probably it's just going to be fun. That's probably what it is. And it has mental in it, too. I guess we need to be a little bit mental, right, to deal with it. Fundamental theorem of calculus. There are kind of two pieces of calculus. One is the derivative, called differential calculus, finding and using derivatives. The other piece we have just entered into that. That's antiderivatives or integral calculus. So differential calculus and integral calculus are related by this theorem. So that's why it's called fundamental. So it relates derivatives and integrals. So we know how they're related. We've done some. We've kind of tried to undo the derivative process by integrating and vice versa. So we know they're kind of inverse operations of one another. And this is the theorem, and it is a theorem, so it does require proof. We're not going to get too involved in the real technical proof, but we'll make it plausible. We'll make sure that we know that it works. But it does interrelate the two kind of halves, so to speak, of calculus. Using the fundamental theorem of calculus is very different from just looking at what it says. It's almost too simple to look at what it says. And this is the way it's stated in your book, the fundamental theorem of calculus. If we have a continuous function, we don't want any holes or breaks or vertical asymptotes. We're going to name a function g of x. It is the antiderivative of f of x. I'm sorry, we do need to keep track of variables here. So if we've got f of t and we're integrating with respect to t, then we're turning around and evaluating that from some number a to some letter x. By the way, when we do that, and we'll look at an example in a second, if you take a function of t and you integrate it and evaluate it from a to x, what are you going to have when you're done? T's or a's or x's?
X's.
X's and a's, right? You're going to have numbers and you're going to have x's because we're through with the t's. We anti-differentiated, then we evaluated. So if that's the function, that's what g of x is equal to, and it is a function of x, right? It has x's in it. We should be able to take the derivative of that function, and we're right back where we started with a subtle difference. We no longer have a function of t. We now have a function of x. Because we differentiated a function of x, we have a function of x. So part of this is switching letters in the process, starting with t's, integrating, evaluating, and then doing what? differentiating. So here's how it interrelates integrals and derivatives. We start with f of t. We're going to end with f of x. Let's track what we do with f of t first. What's the first thing you do to f of t? You integrate it or anti-differentiate it. What's the next thing you do with that result? You differentiate it, right? Because g is an antiderivative. Then we turn around and take the derivative of g, which is itself an antiderivative. What should you get when you differentiate an antiderivative? Whatever you started with. Okay? The only difference is we started with a function of t. Because we switched when we integrated and evaluated to a new letter, x, we end up with a function of x. So if you integrate first and then differentiate, you're right back where you started. That's what this says. And it's a little different when you actually do a problem with it, but that's the crux of what that says. So that's not any new information. This is kind of the one we've been using in this section to this point. If you start with a little f of x, you integrate it and evaluate it from a to b, this is exactly how to do that, how to integrate and evaluate. You take it at the upper limit of integration and you subtract from it what you get at the lower limit of integration. And again, that's only true when the derivative of capital F is little f. So it does relate the two pieces of calculus very nicely. Now the question is, how do we do a problem here? And what are problems that relate to the fundamental theorem of calculus? They're not as pretty as the theorem itself. But before we do a problem that is kind of somewhat generic, let's do one that is has some numbers in it and some letters in it that we will feel comfortable with. So we want to kind of start with this piece of the theorem. Start with a function of t, integrated with respect to t, and we're going to evaluate it from a to x. Let's let a equal 1. Let's let our function of t be t squared. So for this particular example, for this one function only, we're going to go from 1 to x. Our f of t is t squared. Now at the end of the problem, we want to find g prime. But right now, that's what g is equal to. It's an antiderivative of this. Well, what is the integral of t squared with respect to t? T cubed over 3. So after we integrate, we evaluate. So what do we do first? We put in the upper limit of integration. And then we put in the lower limit of integration. So we end up with x cubed over 3 minus 1/3. So we integrated, we evaluated from a number, doesn't matter what number it is, some number a, to some letter. Now the letter here is x, and it's going to take on different things too, like 1 over x and x to the 4th. But right now it's just x, so this is kind of the simplified version. Now what's supposed to be our conclusion? So our conclusion up here is when we take the g prime of x, what are we supposed to get? We're supposed to get a f of x, function of x, that matches this function. It just doesn't have t anymore. It has x instead. So what is the derivative of our result?
X squared.
X squared, right? Is that correct? Derivative of 1/3 x cubed is x squared. Derivative of minus 1/3. So we started with t squared, and we ended with x squared. It's not a mystery. How did we get there? What's the first thing we did with t squared? We anti-differentiated. What's the last thing we did with this quantity? We differentiated. So we ought to be back to the same function. It just changed letters. Changed from t squared to x squared. That's a simple version of the fundamental theorem of calculus. Okay, here's kind of how the author asks this question more often than not when you're dealing with the fundamental theorem of calculus. So they'll say either h of x is equal to this integral, find the derivative of h of x, for the most part, what's the answer going to be? Where are we going to get our answer? If the h of x is the integral of something,
The dot, whatever.
Whatever the function
we're going to
is.
turn right around and take the derivative of that integral. Shouldn't we be back to where we started,
Yeah.
right? So you want to pay particular attention to what occupies the integrand, because that's what we started with. We're going to integrate it and differentiate it. We ought to be back kind of to what we started with. Now, if eventually we're going to take the derivative of what we start with, a lot of times it'll be stated like this. We want a derivative with respect to x of this integral. So I wanted to get a problem that was going to wake Blair up, first of all, so I've accomplished that. Okay, another reason I wanted to get a problem is this has some trig in it, and here's the main reason. That's not x anymore. It's x to the fourth. If you had to guess at an answer right now, we're going to integrate the secant, then we're going to evaluate it, and then we're going to differentiate it. What would you guess the answer would be?
Secant x to the fourth.
Secant of x to the fourth. That's almost correct.
Minus 1.
No, because we're going to differentiate that constant, so it's gone. But you would think it would be secant of x to the fourth. There's a little bit more to it because it's not just x, it's x to the fourth.
4 secant x.
So there's going to be a 4x cubed in there also. Okay, mainly from the chain rule. Now let's see how this works with the chain rule. So this is really chain rule and the fundamental theorem of calculus. So we have this. Let's change it so that it becomes not an x to the fourth here, but something else. That's a function of x, and when we use the chain rule, we set it, our variable, equal to this kind of ugly function of x. So I'm going to change that to a u. I still want to derive this with respect to x, but temporarily our u, and we're going to do a lot of this in the very next section of the textbook, so this is kind of getting us started to making these kinds of substitutions. So I've replaced our ugly upper limit x to the fourth with something that's a little easier on the eyes. It's not x, it can't be x, because I've already got a function of x, so I'm just choosing another letter. It's u. So let's track what we've got here and how we can get to the next step. So we're going to integrate this thing. By the way, this is not easy to integrate. It is integrable, but there's a little trick to this problem. I used that word that you liked yesterday, integrable. We integrate it. What's the next thing we do? We evaluate it from 1 to u. Well, we've got this answer now in terms of u, right? And we're trying to derive it with respect to x. How do you derive something that has u's in it when the variable we're deriving it with respect to is something other than u?
Take the derivative.
The chain rule. That's how we do it, right? We derive that thing with respect to u, and then we derive u with respect to x. So we've got a function of u here. So we're going to derive this thing with respect to u, and then we'll multiply that by the derivative of u with respect to x. Do you see the du's kind of knocking each other out?
Yeah.
And we're back to where we were at the step before. So this is a function of u. We're going to derive it with respect to u. And then to fulfill the conditions of the chain rule, we'll derive u with respect to x. So in terms of this piece of the problem, we integrated this. We evaluated it from 1 to u. This is letter perfect fundamental theorem of calculus, except the only difference is we have a u where there's normally an x. So we're going to integrate it, then evaluate it. Isn't this answer in terms of u? Right? We started with secant t. We integrated. We evaluated in terms of u. We're differentiating with respect to u. We have an answer in terms of u. What's that answer? Isn't it secant of u? We integrated secant, and then we differentiated our result. We ought to be back to what we started with. Not t anymore. It's a function of u. And then we're going to multiply that by the derivative of u with respect to x. Well, what does that mean on this problem? What's the secant of u? What?
U squared.
Oh, the derivative of the u.
U temporarily represented x to the 4th, so that's really secant of x to the 4th. And what's the derivative of x to the 4th with respect to x?
4x cubed.
4x cubed. So there's that little extra baggage that comes along with the fact that we didn't have x here. We had x to the 4th. So it is primarily what everybody said it was going to be. It was the secant of this new variable, x to the 4th. But when it's something other than just x, you have to include its derivative because of the chain rule. So how simple can it be? Let's do another problem without kind of all this working around. We can kind of go directly to an answer. Nicole.
There's a weather sign problem a lot like this. If we have time, do you think we can maybe do that?
We don't have time today, but we'll have time tomorrow. We can actually start. Is it due tonight?
Yeah.
Due tonight?
No.
I don't think it's due tonight.
Oh, okay. Yeah.
Okay. See that? Oh, that's relief. That look on your face. Not due tonight? That's good. Let's get a really ugly looking problem.
I mean, they can put some organic chem.
All right. Y is equal to this. It's going to be a number down here. That number is irrelevant because you're going to derive that portion and it's going to disappear. Got some function of t in here. That's a pretty ugly function of t. So that's what y is equal to. We want to derive y. So what's the first thing we do to this ugly thing? We anti-differentiate it. What's the last thing we do to our result? We derive it. Okay? If we integrate it and then take the derivative of it, we ought to be back where we started, but we have it now in terms of the new variable. What's the new variable?
U.
It's actually square root of x. So wherever there's a t, there should now be a square root of x. What else? What did we just find out happened because it's not just x? The chain rule, and what is the derivative of the square root of x? 1 half x to the negative a half.
1 over 2 square root x.
And then we could possibly put some things together, right? There's the 1 half. X to the negative a half is x to the 1 half in the denominator. And then whatever is kind of allowed at that point we can actually do. But you don't have to go through every little step like we did before. Just allow for the fact that when this is not just x or t or u or r, allow for its derivative in the chain rule. Yes, Mandy.
You get the square root of 2.
Yeah.
He didn't mean that as x.
Oh, that's an X.
Oh, square root of x.
Okay.
There we go. Thank you. Correction. All right, there's just a tiny bit more we need to do, but that's the bulk of the fundamental theorem of calculus, and I will see you tomorrow. Those of you that came in late, make sure I get your absence corrected.